Hello, my lovely students. So now we're going to take a look at section 5.4. What we have in the book is it goes a little more in depth into all of the different pretty picture graphs you can get in polar coordinates. And it does cover this idea of symmetry. All of this is from the perspective of if you have to graph a polar equation by hand, then it's nice to know if there's symmetry. So if it's symmetric, what we would normally call across the x-axis, then that's half as many points you have to draw. So yeah, there's a symmetry across the theta equals pi over 2 line, which is the y-axis. So what you're doing is you're plugging in different versions of a negative on the r or the theta into the polar equation and then seeing if you get the original equation back out. We're not actually going to use these tests. This is more of a hey, these are things that exist. So now you have that somewhere in your brain if you ever need them. Yeah, it's a big if. And a lot of graphs are either symmetric across the x or the y, just because they are like a cosine only graph or a sine only graph. So that cosine on the unit circle is the same top versus bottom. Sine on the unit circle is the same right versus left. Sort of. There was a thought in there. All right. Realistically, if you're going to have to graph those things, put it on something like Desmos, get a look at the picture. So there's one section in Cal 1 and one section in Cal 2 where you might touch on this. And that is when you're learning the new operations in calculus, then you can also apply them to other ways of coordinate systems, which would be polar. Like I said, there are some applications for polar coordinates that make sense. And so knowing that you can use these skills in those areas is helpful if you're going into those areas. Okay. So on a rectangular graph, we perceive movement on it as the x value increases, we go from left to right, because that is how the movement on the x-axis would go. The negatives are on the left, positives are on the right. In polar graphs, it's a little bit weirder. So we have movement through the angles. So I start with theta equals 0, wherever that ends up, and then theta equals the next angle, the next angle, the next angle. And so our pictures don't plot, it's not a left to right thing anymore. It's a circular motion. So when we talk about functions in that sense, it also gets a little weird because now it's not a vertical line test. It's more like a sonar test or man, now I can't remember the name of it. But instead of does a vertical line hit it more than once, you're actually putting a line on the origin, spinning it around, and seeing if you get extra values or not. But when they show up in Cal 2 and even in Cal 1, a lot of times what you focus on is where are the zeros, where are the highs and the lows. And that involves your trig knowledge that we're getting here. So that's what we're going to look at. So our first one here is just how can we find zeros? How can we find maxes and mins? So let's talk about what a zero even is. So when we have this polar equation, the graph will be on theta equals 0 when theta equals 0. Like that's not the kind of 0 we're talking about. What we're talking about is when does the radius equal 0? Like when does all the stuff on the other side coalesce to form a 0 for the radius? Because what the graph has to do is some graphs will start on the 0, others won't. It'll go out and do a thing, but when it hits another 0, the graph has to come back to the center. Then it can go out and do another thing, but if there's another 0, it has to come back to the center. So on polar graphs, if you can figure out where these zeros are, at the very least, you've got a feel for, well, the graph went out and had to come back, and it went out and had to come back, went out and had to come back. Now, for some graphs, they're going to trace the same path over and over again. So you may get multiple zeros, but then you may discover like, oh, this just graphs a circle like 4 times. But knowing where the zeros are, where the maxes and mins are the points where interesting stuff happens and the points you need to know in order to set your bounds in Calculus 2 when you're figuring out areas. All right, so our zeros, this is focusing on when is r equal to 0. And so we literally put 0 in place of r. And now you remember that section where you had to solve all the trig equations? Here's why. So we now have an equation that is asking us, when does sine theta equal 0? Well, we know at 0, sine is 0, so when theta equals 0, and when theta equals pi, plus 2 pi k. So I plug in theta equals 0, sine of 0 is 0, 2 times 0 is still 0. So this graph actually does start at 0, 0. R equals 0, theta equals 0. Then it does a thing, and then eventually it comes to pi, and it's back at 0. So this graph does something between 0 and pi. I don't necessarily know what, but it does this little thing, and then it comes back. And then from pi to 2 pi would be our next 0. It does a thing, and it may do the same thing, or it may do something else. Just depends on how it comes out. So this is the kind of thing in Desmos you can actually play around with typing in these equations and then like, what happens if I put a plus here? What happens if I put a minus here? Like you can actually get really fast feedback on what do these graphs do. That was just completely and totally lacking when I was in school. All right, so they go back into all of the pretty picture formulas with more details. We're not going to ask you guys to use these, but they're here if you were curious, like, well, if we have a cosine graph, it's going to graph a circle like on the around the x-axis on the right or the left. If it's a sine graph, like just a sine theta, then it graphs a circle above or below. Some of these have applications, but it's one of those like very special, specific circumstances that I am not really aware of. So in math, this was literally the, oh, look, pretty pictures, and that was it. So here's where cardioid graphs come from. It's when we have a number plus a number times cosine or a number plus a number times sine. But here, cardioids happen when a over b is 1. So it'd have to be like 2 plus 2 cosine theta, or 1 negative 1 plus, or no, it does say they have to be positive, but like 1 minus 1 cosine theta. Another type of graph we get are these one loop limacons, or dimpled, and the dimple is like that little divot. And so, like, which side the divot ends up on, it's kind of like this short side and then this larger side. And that's because there's going to be a difference between A and B. So A is bigger than B, but the ratio of them is still between 1 and 2. Now, this is different from we go down here, and now B is bigger than A. We're going to get, it's like a cardioid, but has an extra little loop inside. So it's going to pass through the pole, which is the origin, twice, once for the outer loop and once for the inner loop. And this odd duality in here is why this is a favorite for Cal 2, is if they ask you, like, what area does this graph cover? You have to know how to set your bounds and how to, like, think about how it sweeps out. So it's not just as simple as, oh, let's just do 0 to 2 pi and see what we get. You actually have to solve and figure out these zeros, and that is algebra and trig knowledge. So that's what we're going to start with here. So I don't expect you guys to have to graph these by hand, but Desmos just poof, there's the graph. So you're not seeing what happens as you're plugging in the points over time. So we're going to find the zeros for this guy. And then I've got an extra list of numbers, and we're going to actually plot this out and see, like, where does it start? How does it go through all the points? And there's something in the writing assignment like this. So that's the other reason I'm doing it. All right, so let's start with our 0. All right, so 0 equals 2 plus 5 cosine theta. So we minus the 2. And divide by the 5. I'm going to flip my order. So I have cosine of theta equals negative 2/5. All right, so this negative 2/5 is not a number on our pretty unit circle chart. So this is not a pretty angle answer. This is going to be some ugly numbers. But they are numbers we can figure out. But remember, in trig functions, there's always 2 spots where a thing happens. So we want to think about our, all students take calculus. Cosine is positive in quadrants 1 and 4. This is negative. So I'm going to have a quadrant 2 and a quadrant 3 angle that make this guy true. All right. Now, when we graph these, we typically are doing it in radians. I am actually going to get both numbers because it's hard to get a feel for, like, where is this number in radians versus where is this number in degrees. It takes some getting used to the numbers to be able to think about the radians in that way. Okay. So, calculator. So let me start with degrees. So we're doing the inverse cosine of negative 2/5. All right, so in degrees, this is about 113.57 blah, blah, blah degrees. All right, now I'm going to flip it to radians. Go back to the thing I just typed, and this tells me it is about 1.98 radians. All right, so 113 degrees is in quadrant 2. It's between 90 and 180. I need to figure out what's the quadrant 3 angle that matches this, and it gets a little weird. All right, so here's our quadrant 2 guy. Here's the quadrant 3 guy. So those two things that I just highlighted in orange, the reference angles are the same. I don't want to call those theta, but here we'll just say alpha. So those two little guys are the same. Theta is there. So I need to figure out what this little alpha measure is. And then I'm going to take 180 degrees and add that alpha to 180 to get where this green line is. So to figure out alpha, I'm going to take 180 degrees minus my theta. So I've got alpha is 180 degrees minus theta. And then I guess I need a different name for the other angle. So I guess we'll just go with theta prime. Theta prime, which is, let's go with a different color. Is going to be 180 degrees plus alpha. So I could actually put this in here. It just gets weird. In my brain, it actually makes sense to leave this as two separate steps. All right, so I do 180 minus my degree answer. I get 66.42 degrees. So then my theta prime is that plus 180, which is about 246 degrees. 246.42. Now, as radians, two ways to go from here. We really only care what theta prime is in radians. So we could just convert that, but 246.2 degrees. So this is in degrees, so I want to divide by 180 and multiply by pi. So this is about 4.3 radians. All right. So these are some very weird numbers. They're not on our normal unit circle list of points. And that's just because the original equation was weird. Now, our expected high and low values are dependent on cosine. Remember, cosine is a periodic function. So we know where the highs happen. We know where the lows happen. We're just going to plug those in and see what happens. So cosine actually starts at a high value. So we have this question of when theta is 0, R is what? So cosine of 0 is 1. So we would have 2 plus 5. So we get 7 as our biggest radius number at 0 degrees. So that means the point, the r theta point, is 7 comma 0. Our two things that we figured out up here are when r was 0. So we have a 0 at 1.98 radians And then we also have a 0 at 4.3 radians. Now the radius is 0 there, so those are not like, I don't have to go find those points, but what it does tell me is like I start at what I start at, and then up until that 1.98 radians, like my radiuses will all be positive. Then I hit 1.98, and between 1.98 and 4.3, my radiuses will all be either positive again or negative. Then 4.3 back to the starting point should be 0 and 2 pi produce the same point. So then it's, all right, what does it do for the rest? All right, so there is our max being a relative term. And then our minimum value would be from pi. This cosine is -1 at pi. So we are going to have 2 minus 5 will be -3. So our radius goes from 7 to -3. So it's crossing some zeros in there. So this graph is going to do some crazy. So 7, 0, and then we also have -3 pi. So we got some points to draw. We also have a lovely list, including those two maximal minimal values, but we also have our very weird zeros. Those are a little harder to fit in here. So this is why I had the degrees, because I never remember, like 2 pi over 3 is how many radians? I don't know. But 2 pi over 3 is 120 degrees. And you can also see the radius goes from 2 to a negative number. So there's a 0 there. And then over here, there's a 0 there. All right, so I've got this list of points, and we're just going to practice plotting these as points, but remembering, like, as we plot them, those dots are going to get connected in the order we put them down. So we're going to put a few and then connect, and put a few more and connect. Otherwise, you just get a whole mess of dots, and then you're like, what happened? Okay, so we start at 7, which is not on this particular picture, but we'll go about there. Then at pi over 6, which is 30 degrees, we are a little past 6. At pi over 3, which is 60 degrees, we're at 1, 2, 4.5. And then at pi over 2, we're only at 2. All right, so we're seeing here, and remember that 7 we found was the max, so the radius will not get bigger than 7, so that like r equals 7 circle, our graph will be completely contained inside that circle. So we don't want this to like go outward like it's a heart. It's not. It's going to just come in. All right. Now we have at 2 pi over 3, which is 120, we have -0.5. So that is on our 300 line. Right in here. So there's probably still a few more positive points in there. Like it's not all hugging the line, but I can't draw. All right. So now at 5 pi over 6, which is 150, we are at negative 2.3. All right. So 150, we're negative. So that's 330 negative 2.3 will be about there. All right. And then our at pi, we're at negative 3. So pi is normally on the left, the negative x-axis, but then we're counting negative 3. So we actually end up at the point positive 3, 0. All right. So that is half of the points. Now look at what happens with the rest of the y values, or the r values, sorry. We go back through all of the same numbers. And what this shows us is this is a graph that's symmetric top bottom, which is across the polar axis, the x-axis. So I can like top bottom mirror image this to get the rest of the graph. So somewhere about there. It's like there. It'll hit the 0 and be down here. So here, here, like that. All right, and then our 60 is our 300 line down here. What was it? 4.5. And then our 30 line was a little over 6. And then we're back to our 7. All right, and we've come back to where we started. So more values of theta will just trace the same path. Now, in some crazier ways to graph things, noting the direction that you go around the graph is important. And it is important to kind of understand that movement in Cal 2 when you're just saying, okay, I want to know just from this point to this point, and you have to be able to figure out what those bounds are in the angles. So it'd be like from 0 to that ugly 1.98 radians. That is the outer curve. Then from 1.98 to pi, we got that bottom part of the inner loop. From pi to the 4.3, we get the top part of the inner loop. And then from 4.3 back out to 2 pi, we get the bottom half of the outer loop. So just being able to do some like paper math and figure out where those points are is useful, because I could not make Desmos show me points on the graph. It was very annoying. I'm sure there are other graphing utilities out there that will do pretty things like that, but I am not as familiar with them. So that is like the nitty gritty rough, like how you graph polar stuff by hand, which is important if you're going to do some sort of math with polar stuff and you need to know where zeros are, where highs are, where lows are. The only other thing the book had was this very peculiar yet interesting graph. It's called the Archimedes spiral. And if we graph a very simple looking equation, r equals theta, we get a spiral. So as theta gets bigger and bigger, r gets bigger and bigger. So instead of our cosine theta and sine thetas that force r into a cyclical pattern, it just lets it keep going, and it will keep going and going and going. So I just thought that was interesting. Not anything you're going to be tested over. It's just more of a mathematical, like, oh, That's all I get.